Welcome to Mixed Signal Electronics. Good morning. One announcement, although we are near Christmas next week, we have the Mixed Signal lecture on Monday morning next week. I know it's only a couple of days to Christmas, but we already missed one lecture due to public holiday, and we have still lots of material to discuss, and hence I'd like to have this lecture next week also. Today, I want to start with the Nyquist Rate digital to analog converters. The basic idea of a Nyquist Rate digital to analog converter is to generate all possible output voltages that we may generate with this device. So you remember we have DAC that converts a binary input word given here into an output voltage, and the scaling factor is the so-called reference voltage. So what we want to achieve is a V out equal to Vref times the binary input word B in. And you remember this was defined as Vref times B1 2 to the power of minus 1 plus B2 2 to the power of minus 2, and so on and so on. So B3 2 to the power of minus 3 plus ... And as I already said, the basic and straightforward idea is to say, okay, we generate all output voltages that are possible according to this equation. So we generate and then in the second step, we use switches to select the desired output voltage and to connect it to the output. So we use switches to connect the desired output voltage, or let's say the desired voltage to the output. Well, you might say this is a brute force approach that requires lots of effort. However, here you can see the advantages of integrated microelectronics. In integrated designs, it's possible to generate lots of different voltages and lots of signals. Well, of course, this is not the best approach if you want to go for very high number of bits, but for 6 to 8 bits, this is a feasible approach. And so we generate all of these 2 to the power of n voltages and connect the desired one to the output. So the question is, how can we generate all these voltages? Any idea? What is the easiest way to generate all these voltages? So, the comment I usually give in this course is you have to think much simpler and easier than you might imagine. If you think back to one of your basic courses, then one of the first circuits you saw is the resistive voltage divider. And of course, this is what we can use to generate all these output voltages. So in this circuit, we have first a reference voltage here. Here we have a ground signal. And then we connect this string of resistors in between Vref and ground. So if these resistors are all the same, then you can see we have here 1, 2, 3, 4, 5, 6, 7, 8 resistors. So the voltages we have here is 0. Here we have 1 over 8. Here I say times Vref. Here we have 2 over 8, 3 over 8, and so on. 4 over 8, 5 over 8, 6 over 8, and 7 over 8. So it's always over 8, so obviously we have 8 potential values. So this is a 3-bit resistor string converter. We have 3-bit. And you can recognize the scaling that we already saw in this step function. You can see we do not reach the Vref completely. We are 1 VLSB, which is Vref over 2 to the power of n below the reference voltage. So we have a VLSB equal to Vref over 2 to the power of n, which is in our case 1 over 8 times Vref. By doing this, we have generated all voltages at these nodes. So one important point to remember all the time, if you use a resistive voltage divider, what is important to make these divider ratios valid? For instance, here we have one of 2 resistors. Okay? Here we have 0, here we have Vref. This is R, this is R, so we have here 1 over 2R. Is this valid all the time? No, guys, okay? This is only valid if no current is flowing here, okay? We say if the voltage divider is not loaded. So the voltage divider is a good way to generate voltages or derive fractions from a reference voltage. However, we have always to assure that no current is flowing or only a negligible current is flowing out of the voltage divider. Okay. What about the rest of the circuit? You can see that there are switches that connect all these voltages to a common node. This is a so-called voltage bus. And we connect all these signals to this bus. And now you can see, of course, in order not to cause a short circuit, it is required that only one switch is conducting at a time. So we have 2 to the power of n switches, but only one is allowed to conduct. So we can also say the control signal is 1 hot-coded because only one signal enables a switch and is active. Then we may enable any of these switches. So the respective voltage is connected to the voltage bus, and this signal is then fed to an operational amplifier which is configured as voltage follower. And this is very important because this exactly assures the requirement that no current is drawn out of the resistive voltage divider, out of the resistor string. So we have here a voltage follower as buffer. This is a buffer. So what we did is we generated the voltages with a resistive voltage divider. and we use these switches to select one of these voltages. So what do you think is a requirement for the reference voltage to make this circuit work? The switches here should work as real analog switches. So you know that an NMOS transistor can act only as a switch if the control voltage is high enough. So the highest voltage that can occur is at this node. So we have the situation that the max voltage is 7/8. The control voltage at the gate here is the highest voltage we can use here. So it's, let's call it VDD. So we have the situation that we have VDD minus 7/8 times Vref. So this is minus Vref minus 1/n times Vref. This is the gate to source voltage that we see at this transistor. VDD minus this term. And this has to be larger than the threshold voltage. Larger than V threshold. So we can say Vref has to be smaller than 1/1 minus 2 to the power of minus n VDD minus V threshold. What can we do if we want to go for a higher voltage range? I guess we discussed this when we talked about MOS transistor as switches. So there we saw that the NMOS transistor is a good device to switch small voltages. A PMOS transistor on the other side is a good device to switch high voltages. So what you can do here is that you either mix NMOS and PMOS, or that you use complete transmission gates that can switch both small and high voltages. And the price for using transmission gates, we will see this on the next slides, is of course that we have higher parasitic capacitance, so we will slow down the circuit by doing this. Okay. One drawback of this device is, you can see here, the output voltage corresponds here always to the input voltage of this operational amplifier. So this means that we need a buffer or operational amplifier that has a high input common mode range. So a high input common mode, which makes the design of this device much more difficult than if you would use it always in a situation where you have a virtual ground or not a virtual ground, an analog ground connected to one node, and the input signal is always around the same common mode range. Here the voltage at the input differential pair can vary a lot, and this makes the design of this device challenging. The question I want to discuss with you guys on the next slide is, how fast can this DAC settle? So how fast can we go with this device? So to answer this question, of course, extensive simulation of this device would be required. However, it is often useful to have a rough or a technique to roughly estimate the delay of such a circuit. Here it's not important that we have best accuracy. If we need accuracy, we can do analog simulation. However, if we just want to compare different architectures, And in order to get the feeling of the trade-offs and what makes a circuit fast, what makes a circuit slow, it is enough to have a formula to roughly estimate the delay. And one technique to do this is the so-called ELMO delay, and the people that have been in my digital lecture already know this formula. I have it in this course too, because it's also very useful to estimate the delay of these type of DACs. So the ELMO delay requires some prerequisites. It can be applied to circuits similar to that one shown here, to circuits with R's and C's that fulfill the requirement that we have one input, that we have caps from each node to ground, and that we have no resistive loops. So a resistive loop would be if we have here a resistor to this node, for instance, then we would have here a resistive loop. So this should be avoided. And if this is the case, then we have always exactly one path from each node back to the input. So for instance, if we go from this node to the input, and you can see there is exactly one path from the node to the input. And the sum of all resistors that we pass along this path is called the path resistance. So the path resistance is the sum of all resistors on our way from the input to the node under consideration. Then we can go one step further and can say, okay, let's look at two different nodes. Let's look at this node, for instance, and at this node, for instance. And again, we draw both paths from these nodes to the input. This is this one, and this is this one. And here you can see we have now a fraction of this path that is common to the green and the red. This is this subpath. And then there is a subpath that belongs only to the red or only to the green path. So the joint path resistance, and I have it, the shared path resistance is the sum of all resistors that lie in the common part of both paths. So we have this resistor and this resistor that belongs to both paths, and hence they sum up for the shared path resistance. Using these definitions, we can define the ELMO delay. And the formula for the ELMO delay looks a little bit complicated at the first view, but actually it is not. So what we do is that we build a sum over all nodes. So we go over all nodes, and we calculate for each node a time constant given by the node capacitance and the joint path resistance from this node to the input. So then you might ask, joint path resistance requires a second path. Yes, if you are interested in a delay from this input to a certain output, then this defines the reference path. And for the ELMO delay, you then go over all caps, and the time constant is given by the cap times the joint path resistance of the node under consideration. So this one, for instance, this one, for instance, and the path, the delay path that you are interested in. So let's make simply an example for this. So we are interested in the delay. Let me check if I have another foil. No. If we are interested in the delay from the node S to this node I, then we start our sum and say, okay, first we look at this cap. So our tau is given by C1, and the resistor from this node to the input that is common to the red path is only the R1, so we have C1 times R1. Okay, then we go to the next cap, plus this guy is C2. The path now is like this, and only the R1 belongs to the blue and to the red path. So here again we have to multiply by R1. Then we go for C3. So plus C3 times, and now we have here the R3 and the R1 in the common path. So we have now R1 plus R3. Here for this C4, we have this path. You can see that only the R1 and the R3 are in the common path. So we have here R1 plus R3. And finally, our last cap is the CI. And for the CI, of course, there is only one path left. This is R1 plus R3 plus Ri. This is the formal definition of this, and now we can apply this to our resistor string deck. Let me skip this one. So, we have to understand that the switches have an on resistance and the switches also have a parasitic capacitance. So I guess the on resistance is quite clear what is meant here. Is it also clear why a transistor or a off-mode transistor still has some parasitic capacitance? Is this clear? Otherwise I make a small drawing to explain this. Drawing? Okay. So let's assume this is your transistor. This is your gate. This transistor may be turned off, VSS. And then this is the node that is here connected to all these transistors. Okay, here we have our voltage bus. So this one is connected here. So now we have a parasitic capacitance, a so-called overlap capacitance from the gate to this drain region. We have here a parasitic diode from this node to this node or to the bulk, which also causes parasitic capacitance. And of course we have wiring capacitance here. So we can simply say each transistor contributes a certain amount of capacitance. And this means that if we look at this path, for instance, we have our on resistance of the transistor. So one transistor is turned on, for instance this one. Then we have, before we go to the op amp, we have here a parasitic capacitance as the sum of all transistor caps. So we have here 2 to the power of n times a parasitic capacitance, let's call it CT, C transistor. And important is that we have 2 to the power of n of these guys. Then we have here the on resistance of the transistor, RT. This was CT. And then let's say we have an effective resistance of this resistor string. So let's call this R string. So we can then say, okay, the ELMO delay estimation so in this case it's pretty simple because we have or mainly one node, which is this one. So the delay estimation is the cap that we have at this node, which is 2 to the power of n times CT, multiplied by the path resistance, which is R string, plus R transistor. So I neglected all the caps in this string because they are already charged. Okay, so if we apply the reference voltage, then the voltage divider starts working, charges up all these intermediate caps, so I neglected this. But this cap, of course, is the one that you have, or where you have to change the charge always if you toggle these switches. So if you change the input of your DAC, you turn on another switch, so you have to change the charge on this cap, and this requires a setting time that can be estimated by this ELMO delay. Of course, there is also a delay here in this buffer that adds to the overall delay. However, if we only want to compare this DAC core, then it's enough to have this, because the buffer is usually there in all different types of DACs. Okay, before I start with the second DAC architecture, I'd like to ask you to fill out the evaluation sheets. And Michael and I started this morning to find out the right sheets of mixed pile of different sheets. So please make sure that you have a lecture on your evaluation sheet, not lab or not Hauptseminar or whatever, but it's mixed signal lecture, so you should fill out the right one. Then one comment that is each year mixed up by some people. So make sure what means good and what means bad. So sometimes I get very good feedback at the comments, and I get very poor feedback here because it's mixed up. So make sure what is completely disagree or completely agree. Then another comment is, please also use these 2 comment fields, because this is even more valuable for me to improve the quality of this lecture. So this here is statistics. This is used to compare all the lectures of our faculty against each other. But if you want to give feedback, want to say, I like this, I didn't like this, and you should change this and this, then please put this here in these common fields. Okay, Michael, I give this to you. Thank you. Then one comment for the people that are only attending online. I heard that this is quite a lot of people only online. So I'd like these people to take part in the evaluation as well. Evaluation can be done also online, and for doing this, please send me an email, and then I will, excuse me, then I will send you back one of these ID numbers of the evaluation, and with these ID numbers you can take part in the evaluation online. So while you're working on your sheets, I put this down here. Okay, thank you very much. So, next architecture is this type of ADC. Actually, this is one of the earlier, sorry, not ADC, DACs. This is one of the earlier techniques. This is a DAC where you do not have a decoder at all. So if we go back to this one here, you have seen we have a digital decoder that converts the input word, the binary input word, into a one hot coded signal. So we are here binary and we are here one hot coded. In this architecture, you can see that this decoder is missing completely, so we have no decoder logic. Instead, we have now a binary tree of switches which actually acts as a decoder. So let's start with the MSB. You can see we can partition all our voltages in two parts. So we have here all the lower voltages. Here we have all the higher voltages. And we use the MSB to select the output voltage is in the upper range or is in the lower range. So this is done by these two switches. So if the B1, the MSB is high, we select the lower part of the tree, or if the B1 is low, then the B1 inverse is high and we enable the lower part of these voltages. Then we can use the second bit in order to search or select voltages in either the upper or the lower part. So the next voltage is subdivided here. So we subdivide either the lower part into subparts or the higher part into subparts, and we use the second bit in order to select either the higher subpart or the lower subpart. Or if the MSB has selected the lower part, then we use the MSB to use this part or this part, not the MSB, the second significant bit. And then of course we can continue like this and can take the next bit, subdivide the previously selected sub range as well. So we can use now, in this case of a 3-bit DAC, we can use the LSB in order to select the final voltage. I forgot this one, sorry. Good. So we have here a binary tree that acts as a decoder. So the decoder is realized by this tree of switches. Then again, we can use the ELMO delay to estimate the settling time of this DAC. So we can make an ELMO delay estimation. So if we again assume that we enable this path, then I have here the parasitic on resistance of the transistor. Here I have the effective resistance of the complete string. So we have here our string. Then we come to this node, and this node has 3 transistors connected. So we have this one, and this one. So we have effectively here 3 CT. Then we have the parasitic on resistance of another switch, an RT here. At this node we have again 3 transistors, so we can say here also 3 CT. Another parasitic on resistance RT. And here again we have a parasitic resistance. Okay, at this node we have only connected this transistor and this transistor. However, we have also the input capacitance here into this buffer, so we have the parasitic capacitance of this transistor, and the input transistor of the diff pair of the buffer. So we can say also 3 CT. This simplifies the calculation. So our ELMO delay is then the first cap is 3 CT. The resistance seen by this cap is RT and our string. So we have our string plus RT times 3 CT. Then the next one is 3T CT. Then we have a first on resistance, a second on resistance, and our string. So here we have our string plus 2 RT times the same cap, 3 CT. Plus, for the last one, this one is parasitic on resistance, parasitic on resistance, parasitic on resistance, and our string. So we end up with our string plus 3 RT times 3 CT. And we have one of these lines for each bit that we have in the stack. So we can say at the end, if we add all of these guys together, we have n terms. So we have n times our string times 3 CT. So we have 3n our string CT plus, here we have 1, 2, 3 up to n RT, and this brings up to 3 over 2 RT CT n times n plus 1. So if we would compare this to the resistor string converter, then we can see in this case we have the problem that we have several switch transistors in series, which brings up our series resistance. So probably this one is the slower one. Well, this is actually not always true. It depends on the number of bits. So if the number of bits is relatively small, then this one is the slower converter than the resistor string converter, because in the resistor string converter we have only, or in the basic one I showed you, we have only one switch transistor. Here we have already 3. So usually this architecture is known as the faster one. And also we have to say that this decoder logic is nowadays really negligible. So having a couple of gates to do this decoding is, in terms of area and power, really negligible, so we can do this. However, if we go to a higher number of bits, then you can see that this parasitic cap here scales with 2 to the power of n, so scales much faster than in the other case. So for a higher number of bit, the speed advantage of this architecture is reversed, and this architecture may become even slower. However, this type of DACs, either this one or this one, is usually used for a small or medium number of bits. So this is not the architecture of choice if you want to achieve a high number of bits. Why? Well, because then the effort explodes, because for each step you need a resistor and you need a switch transistor, or you may need even more switch transistors in this tree architecture. And then there are other architectures, so-called binary weighted architectures, that I also discuss today, that can be used instead. Okay, the question is, how can we combine the advantage of these two architectures? How can we use or achieve a relatively small load cap, and how can we reduce the effort for the decoder? And by searching such an architecture, people ended up with this so-called folded resistor string converter. You can imagine this as just taking the original structure and bending it in a meander form like this. So take the original resistor string converter and then start from the reference voltage. And then here you see you have all these resistors. Then you bend it and stretch the line a little bit, go back, and then you have the next row. You go back, and then you have the next row. You go back, and then you have the next row. So this can be also seen as just a way to reshape the original structure. Well, by doing this, we get a much more, or a rectangular shape of the circuit with a much better aspect ratio, which is also an advantage for integration. But we can also use a more advanced scheme to control the switches. And if you look at the circuit, you can see now we have two decoders. We have a so-called row decoder, and we have a column decoder. Both of these decoders have now only half the number of bits that we would use in a basic resistor string. So here we have a 4-bit structure, but you can see that we have only 2 bits at the row decoder and only 2 bits at the column decoder. So what the column decoder does is to select exactly what the row decoder does is to select exactly one row. So let's assume this as an example. So we say this is the row 1, 0, whereas this is 0, 0, 0, 1, 1, 1. And by enabling this row, we turn on all these transistors. So by turning on all these transistors, we connect the respective voltage here and here and here to this column. All the other transistors in a certain column, for instance this one or this one and this one, are disabled. So this column here is only connected by this device to a certain voltage out of the resistor string. And then we use a select device for choosing one column. So we're using this device to connect the red column here to this bus here. So this is an access scheme as you probably know it from memories. In memories we call this a word line. Then we turn on one word line, enable all cells in the respective row. We call this a bit line. So the memory content is applied to this bit line, and then we have a column decoder and a multiplexer that selects one of a set of bit lines and connects it to the output. So the advantage here is we bring this down by a factor of 2. So we, as I said, we have here only half the number of bits and here half the number of bits. So this means that we reduce the number of wires here with the square root, and the number of transistors that is actually connected to a certain line is also reduced, because here you can see in this column, for instance, we have connected only 4 devices. Well, then we connected to this bus and we have another 4 devices. So we bring this down and have now only 2 times square root of 2 to the power of n. And the square root is exactly this halving of the number of bits, is 2 to the power of n over 2. So this reduces the effort not only for the decoders, but also reduces the parasitic cap that has to be recharged after the DAC is switched. This is an architecture that can be used to reduce the effort if the number of bits increases. So you know, if the number of bits increases, then I need 2 to the power of n switches and 2 to the power of n resistors. So if we think about a 6-bit structure, this would require 64 switches and would require 64 resistors. Here we have a 2-stage architecture where we have a first stage that is used for a coarse selection of the output voltage and a second stage that does fine adjustment of the output voltage. So how does it work? Here in the first stage of this example we have a 8-tab resistor string. So we have a 3-bit input stage, and let's assume for an example that this switch is closed and this switch connects here 3/8 times Vref to a first bus, and then we close a second switch, and the second switch is a neighbor of the first one. Let's say this one, we have here a 4/8 times Vref. Okay, you can't read the Vref, sorry, I removed this again. Let's say only this is 3/8. This is 4/8 times Vref. And we connect this voltage to a second bus. So now we have taken 2 neighboring voltages of this resistor string. So the difference here is 1/8. Next step is that we use buffers to copy this voltage, and the second buffer to copy the second voltage. So we have now a copy of these two voltages, which leads to a voltage drop here of between these 2 points of 1/8 times Vref. And now we use a second resistor string. And this second resistor string subdivides this 1/8 times Vref again. Let's assume as an example that we close this switch and connect it to the output buffer. Well, the voltage that we have from this node excuse me, from this node to this node, this is 0, 1, 2, 3, 4, 5, 6/8 times the voltage we have over the complete string, and this was 1/8 times Vref. This is the voltage from here to here. So question is, what is the complete output voltage? The complete output voltage is this voltage drop here. And then we go over this buffer and we see here, okay, there is another 3/8 times Vref. So our output voltage is 6/8 times 1/8 Vref plus 3/8 Vref, and at the end we have 30/64 times Vref. And this 64 indicates that we have indeed a 6-bit converter here. However, we have not 64 switches and not 64 resistors, but now we have 2 times 8 resistors and switches, so we have now 2 times 2 to the power of n over 2. So here we have considerably reduced the number of switches and resistors. However, the price was that we now have 2 additional buffers. This one that copies the first voltage, this one that copies the second voltage. And of course, these buffers need a good matching in order to achieve that we really have here the voltage or a copy of the voltage difference in between the resistors here. So this voltage difference is here copied to these 2 nodes, and of course therefore we need a good matching to have a good copy of this one. Okay. This has been 3 or 4 architectures for resistor string based DACs. And you have seen as soon as we increase the number of bits, the effort explodes with this exponential. So here we have this 2 to the power of n over 2. In the other architectures we had even 2 to the power of n. Common to all of them is effort increases rapidly if the number of bits goes down. So the question is, how can we achieve a high number of bits with another technique that does not have this enormous effort? So what we did so far is that we said, okay, we generate brute force all possible voltages that can occur in this device. Now we want to say, okay, we can also work in current mode, which means that we first generate currents according to an input signal, then we add all these currents together, and in a third step we convert these currents into a voltage. This is a completely different technique. Old technique was generate all voltages, select the appropriate voltage. Now we say we generate first currents according to input bits, then we add several currents together, and then we convert this into a voltage. And the second thing is that we exploit here is to say, well, the input word is already a binary thing. So why not using binary analog values, so binary scaled currents, and add them together in order to generate the output word? And this is exactly what leads to this binary weighted current mode converter that is shown on this slide. How does it work? You can see here we have several current sources. And these current sources are binary scaled. So we have here a current I, then we have I over 2, I over 4, I over 8. So we could directly say this one corresponds to the most significant bit, this one corresponds to the least significant bit. And by going from one current source to the next current source, the current is always scaled by a factor of 2. And this is the same factor of 2 that we would see if we go from one bit to the next bit. Then we use switches to connect the current source to a common node, depending on whether the respective bit is set or not. So if a certain bit is set, then the current flows into this red node. If the bit is not set, then the current does not flow in this red node. So by a structure like this, we add all these currents together because the total current flowing here is given by IF equal to B1I plus 1 over 2 B2I plus 1 over 4 B3I plus 1 over 8 B4I. So here again you see this binary scaling. And this is the sum current that flows here. So you might say, well, we want a DAC that generates a voltage, not a current. Here we have a current that represents the input word, and we can convert this current into a voltage by forcing this current through the feedback resistance of this op-amp. So here this current causes a voltage drop given by RF IF, and this corresponds exactly to the output voltage. Here we have RF IF. You can see that we have a ratio of the maximum current to the minimum current equal to 2 to the power of n minus 1. So here the current is much bigger obviously than the current here. So also the symbol for the switches is the same for all of these current sources. Probably we need a much larger switch here than here, because this one has to bridge a much higher current, and to make the voltage drop the same, we have to scale up the switches. So the switches are usually scaled from here to here. Well, then also look at this switch structure. Looks a little bit strange. Here it would be, for the operating principle, it would be sufficient if you would say, okay, I connect the current source to this node if the respective bit is set, or I disconnect the current source from the node. Why is this second connection here, that the current source is toggled between the virtual ground of the op-amp, which is here, and an analog ground here? Why is this? Any idea? Pardon me? A little bit louder, please. Yes. Why do exactly. So the point is, if I have a current source, let's start with an ideal current source, then this current source wants to sink the respective current. So let's assume we have here an ideal current source, and this current source can be connected here to our collecting bus, and it sinks a certain current I here. Well, if I would disconnect it here, the current source still wants to sink this current. If it is connected to nothing, then in the ideal case we have an unallowed situation. So we can connect it here also to an analog ground. Then the current source always sees the same potential. Here it sees the virtual ground. Here it sees the analog ground. From a potential perspective, this is the same. So it can, in both situations, sink the same current. Otherwise, again, if I disconnect it here only and connect it to nothing, current source wants to sink this current, we have over idealized situation, which is not possible. So let's look at a real current source. A real current source is in the most basic case a transistor. For instance, something like this. Okay, here we have a current mirror. This is our current source here. Well, in order for this device to be a good current, or to be a current source, not only to be a good one, to be a current source, it requires that we have this transistor here always in saturation, which means that we need at least one VD sat here. Okay? And then we can have this, this switch that connects it to our bus. If I toggle the switch and switch it to nothing, then there is no current that can flow. So the current source still wants to sink this current, so it cannot sink the current anymore, and hence the voltage here drops down. The voltage drops down until the drain source voltage of this device here is 0. And then the current stops flowing. Of course, then it is not a current source anymore, because the requirement this device has to be in saturation is not fulfilled anymore. Well, would be possible, but then if I connect the switch back and want the device again to work as a current source, then first I have to bring up this voltage, and first I have to bring this device into saturation, which consumes a considerable amount of time and also causes transients, because at the beginning the current is 0, then it comes up, so everything settles very slowly in the DAC. However, if I connect this here to an analog ground, then the current, so actually this is an analog ground, this is a VSS. Then the potential from here to here, or the potential here and here, is the same. So there's only a small amount of time while I switch from one node to the other one where the current cannot flow. And during that time, this voltage cannot drop completely. So I switch fast, then the current can continue to flow. The potential at this node does not change. And if I switch it back, I can provide this current immediately and have a fast settling. So the same holds if you have more complicated implementation of this current source. You can think of this cascade current source or whatever. Situation is always the same. You want to avoid that the current source stops its operation just by disconnecting the current from this node. However, let me go back to this one again. This means the current in the current sources is always flowing, independent of the switch position. The power is also consumed all the time, independent of the switch position. It is only the question where the current is flowing. So sometimes you can also say this is a current steering technique, because you put the current to one node or the other one. Okay. Now we have a binary structure. Let me go back again. Here we have 4-bit. We have not implemented 64. Sorry, not 64. Why 64? Yeah, we have a 4-bit structure, which means that we would require 16 resistors or 16 switches in a resistor string case. Here you see we have only 4 elements, but these elements are binary scaled. So what is a disadvantage of this? And to discuss this, I want to look at the monotonicity of such a structure. Let's assume we have this binary weighting. Then in the ideal case we have a scaling in between the different stages. We have, for instance, here 1i, 1/2, 1/4, 1/8. So let's assume that we have a first input word which is 0, 1, 1, 1, and this would result in an output of 7/8, and then we increment this by 1 LSB, so we have 1, 0, 0, 0, and this leads to 1. Well, I mentioned it several times that we always have some variability in the circuit. So our circuit elements are never exactly the ones that we have designed. Sometimes they're a little bit too large, sometimes a little bit too small. There is some variation. And let's assume that we now have a mismatch of the current sources. So this one is not 1, but is now 6/8. So let's say this is mismatch of current sources. It's happened for some reason. Then we have the same input pattern and say, okay, first we have the 0, 1, 1, 1, and this leads us again to the 7/8. Then we increment this and have now 1, 0, 0, 0. And now you see we have only the first one, which is the 6/8. What happens here? We increment the input. So from here to here, we go up by 1 LSB. And what we expect is that we go also up by 1 VLSB. This happens here. Here we go up by 1 VLSB. However, here you can see we go even down. And this is this non-monotonic behavior I mentioned last week. If we have here our B in, and we have here our V out, then we would expect if we go from one step to the next, we go up. And now what happens is that we go from here to here even down. So this is non-monotonic behavior. Which means if there is a mismatch due to variation, then we can end up in a situation that this device is not monotonic. Well, here of course it's an extreme case that this happens in the MSB is very unlikely. However, this is an easy example to illustrate what can happen here. Okay? Can this happen in a resistor string converter? What do you think? So who thinks non-monotonic behavior can occur in a resistor string converter? Cannot occur? Okay. It's correct. No non-monotonic behavior can occur in a resistor string converter. Why? Well, let's assume we have connected this resistor here to the output. Well, then if I increase the input by 1 LSB, then I go from this switch to this switch. So you can see that the output voltage always increases when I come from this node to this one. The worst thing that can happen is that this resistor becomes 0 because it is shorted or whatever. Then the voltage going from this switch position to this switch position is the same, but it can never go down. This cannot happen here. So the big advantage of the resistor string structures is that they are inherently monotonic. Always if you have binary weighted structures, you have the situation that these non-monotonic behavior can occur. There is another effect that can happen in, or especially in binary weighted DACs, which is a dynamic one. Well, look, if we switch again from 0111 to 1000, let's assume that the control signals of the switches are not, or do not all have the same delay. So what could happen is that the control signal for the MSB is pretty fast. So we get the switches first. All the other bits are still 1. And then a couple of picoseconds later, then also the other bits switch and we go for 1000. Okay. So at the end it's the same, but in the intermediate state we have here all bits set to 1. So what should happen is that we make a 1 VLSB step from here up to here. However, during that intermediate time we have all bits set to 1, which means that the voltage tries to rise to much higher values, and then we toggle the other bits and then it goes towards the final value. But at the end we have a situation that we start from this voltage, then we put all bits equal to 1, so we shoot up, and then after a while the other bits switch, so then we go down again, but at the end we have a kind of overshoot. Or in another situation, the MSB might be too slow. Then we may have an intermediate situation where all bits are 0. And then my signal looks like this. I go down, then the other signals or the MSB switches, and then I go up again. Well, it depends on your application if such glitches at the output are a problem or not. If you require an output signal that makes a clearly defined transition without these large and wrong transients, then this architecture may be not the right one for you. However, you can add something that avoids or at least reduces this effect. What do you think? What can you do in order to get rid of these glitches? What is the requirement? When do the glitches occur? The glitches occur if we have a delay difference or delay uncertainty of these signals. How can we get rid of this one? Well, the requirement is simply, again, think simple. The requirement is all signals have to switch at the same time. Okay, how can we assure that all signals switch at the same time? We need a synchronization element at the interface of the digital decoder and the input of the DAC. So you have your DAC, here you have your DAC. This is this binary weighted structure. Here you have all your input bits. Here you have your reference voltage. And the input bits come out of a certain logic that computes the value for the DAC. And in this computing logic, there may be a short path to one input of the DAC, and there might be a long path to another input of the DAC. And hence, exactly this situation may occur that the switching times are different and these glitches occur. Well, we have always synchronous logic, so somewhere in front of this logic is a register that issues the data into the logic computes the signals for the DAC, and then the DAC converts these signals into an output voltage. Well, to avoid the effect of the different path lengths through the logic and make these signals switching all at the same time, we need a second register here, which is also controlled by a clock signal. And then these signals here switch at the same time. They are synchronized to the clock. Clock signal occurs, all signals switch, and the DAC creates the correct output value. Well, there's still some challenges, because if you distribute the flip-flops for the various bits, then you have to assure that the clock signal arrives at this signal at the same time, but this is straightforward design challenge. In principle, you have solved this issue here. Okay. Which questions do you have concerning today's lecture? Okay. If not, I'd like to ask people who arrived later and did not take part in the evaluation to ask Michael for evaluation sheet and fill this up. Then, because it's so much fun, we have a second evaluation for the tutorials today. Thanks for joining this evaluation as well. I hope that I will see you next Monday. As I said, also it is near to Christmas. We have a mixed signal lecture next Monday. And yeah, till then, I wish you a nice week. See you.